So, good afternoon, everyone, and welcome to the 53rd Annual James R. Killian Jr. Faculty Achievement Award Lecture. I'm Mary Fuller, Chair of the MIT faculty. And before we get started, I'd like to ask that everybody silence their electronic devices. And if you're sitting on the edge of a row, and you can, if you would move towards the middle so that as people come in late, they can easily find a place to sit, right? So it's great to sort of keep some seats at the ends of the rows open for latecomers. Thank you so much. The James R. Killian Jr. Faculty Achievement Award was established in the spring of 1971 as a permanent tribute to James R. Killian Jr., who was president of MIT from 1948 to 1959 and chairman of the corporation from 1959 to 1971. The Killian Award recognizes and celebrates extraordinary achievement by MIT faculty members and communicates their accomplishments to members of the Institute community. The title of Killian Lecturer is the highest honor that the MIT faculty can bestow on a colleague. It is our privilege today to be addressed by John D. Joannopoulos, the Francis Wright Davis Professor of Physics, and since 2006, also Director of the Institute for Soldier Nanotechnologies. Professor Joannopoulos received his PhD from the University of California, Berkeley in 1974 and immediately joined the faculty of the MIT Department of Physics. And so if you do the math, you know that he's celebrating 50 years at MIT this year. Professor Joannopoulos' deep and lasting impact on the field of theoretical condensed matter physics stems from his pioneering work in harnessing ab initio physics to elucidate the behavior of materials at the atomic level. His seminal research in the development of photonic crystals has revolutionized understanding of light-matter interactions, laying the groundwork for transformative advances in diverse fields ranging from telecommunications to biomedical engineering. These remarkable achievements have earned him both national and international recognition, evidenced by the many honors and rewards he has received. These include election to both the National Academy of Sciences and the American Academy of Arts and Sciences. He is a fellow of the American Physical Society and the American Association for the Advancement of Science. Professor Joannopoulos has been a legendary mentor to generations of students, inspiring them to achieve excellence in science while helping them develop practical benefits to society through entrepreneurship. His former graduate students have become academic leaders at top-tier universities and research institutions worldwide. One of Professor Joannopoulos' mentees reached the pinnacle of scientific achievement, being awarded the Nobel Prize in Physics. And other students have gone on to found companies or led successful careers in other areas outside of academia. I also hear that several of them teach at MIT. Professor Joannopoulos has been a role model not only in what he does, but in how he does it. In every collaboration, he casts a wide net so as to value multiple voices, to ensure that everyone feels included, and to encourage partnerships across groups, fields, and institutions. Through the individuals he has taught or mentored directly and their academic descendants, Professor Joannopoulos has had a vast influence on the development of science in recent decades. His passion for impact has also supported the translation of basic science into real-world applications through numerous startups in areas ranging from the development of medical technology to save or improve the lives of hundreds of thousands of patients, to technology with the potential to revolutionize the way devices are powered, from consumer electronics to electric vehicles. His ability to bridge the gap between academia and industry has both advanced scientific knowledge and led to the creation of dozens of new companies, thousands of jobs, and groundbreaking products that continue to benefit society. Finally, translating basic research to benefit the nation's service members has been an area of utmost importance to Professor Joannopoulos throughout his career. John, will you join me at the lectern, please? Thank you so much. John Joannopoulos, it is my privilege to represent the MIT faculty in honoring you with the James R. Killian Jr. Faculty Achievement Award. In doing so, we recognize you as a leader, visionary scientist, beloved mentor, and believer in the goodness of people. Your legendary impact on MIT and the broader scientific community is immeasurable. I think we're supposed to shake hands again. And let me give you the certificate.
Thank you so much.
Yeah.
Thank you so very much. That was a very, very generous citation. I'm extremely honored with this award and extremely flattered because it comes from my colleagues who I admire greatly and who I value greatly. So thank you again very, very much. I can get myself here. All right, so a while back in 1990, there was a editorial by Sir John Maddox, who was the editor of Nature magazine. Nature is one of the premier journals in science, together with Science. Nature and Science, these two journals, in which he wrote, if only it were possible to make materials in which electromagnetic waves cannot propagate at certain frequencies, all kinds of almost magical things would be possible. Since then, there has emerged a new class of materials called photonic crystals. Their emergence is based on some work by Eli Yablonovich and Saziv John. And in a nutshell, it's to try and design artificial materials which can affect the properties of electromagnetic modes, which we can also call photon modes, or we can also, just for simplicity, call photons, in the same way that a semiconductor, a crystalline semiconductor, affects the properties of electrons. Now, if we take a typical semiconductor like silicon, this is a ball and stick, this is a ball and stick model of silicon. And the nuclei are placed on in a periodic arrangement in what's called the diamond lattice. And because of this periodicity, every electron that's associated with this system can be described by two things, an energy and a wave vector. Now, the wave vector is something like a momentum-like object that the particle has. So those two quantities. If you collect all the allowed energies and wave vectors that can exist inside this material, that is called a band structure, and you plot energy versus wave vector as shown here. And the lines, the black lines here, are the allowed values of energy and a wave vector for each electron in the system. And notice, well, there's one more thing. Even though you have periodicity in real space, you also have a kind of periodicity in what's called reciprocal space, which means that suppose I have an electron with a wave vector out here. Well, it doesn't fit in here, but it does really. You can match and bring it back in. What that means is that this box, which is called a Brillouin zone, contains all of your solutions for this particular system. And the important part here is that this particular system, this semiconductor, has a gap, an electronic band gap, an energy range where electrons are not allowed to exist inside the material. So suppose we tried to do something similar now with a bunch of macroscopic material. For example, low index material, macroscopic, and high index material. We need the contrast in this case to give us the periodicity. And because it's periodic, completely periodic, instead of an electronic band structure, we now have a photonic band structure, where every photon in the system has a frequency and a wave vector that exists inside this Brillouin zone. And the interesting thing about photonic crystals is that they can be chosen to be any shape, any size. If we pick something to be on the order of micron size, then we're talking about optical light. It's optical light that will be passing through this material system and be affected by the structure of the system. If we're looking at a larger scale, like centimeter scale, then it's microwave light that'll be passing through, interacting with the system. So we have a lot of flexibility here to play with. And with this flexibility, we can then come up and design a photonic crystal that has a photonic band gap, a range of frequencies where light is not allowed to exist inside the system, unless you break the symmetry. Now we can break the symmetry by simply changing, say, one aspect of the structure. And if we change the symmetry like this, then the photons associated with that particular object can actually exist inside this photonic band gap because we've broken symmetry, so it's possible to exist. If you are, here's a heuristic. Suppose you are a photon associated with this particular defect, and you go very far away from the defect, and you look around, and you see a perfect crystal, but your energy is in the gap. It's not supposed to be there. So the only place that you can be is localized around that defect itself, so that a defect like this one object can act like a microcavity to localize light. If you take and you make it a line, then it could be a linear waveguide to localize light. These are new mechanisms for dealing with, light in nature. So I'd like, and this is what I'm going to focus on today. I want to give you, there are several, there's more than several. Over the years, there's quite a few examples that we've discovered of very anomalous, strange behavior of light that cannot exist with normal optics. I'm going to show you now 4 examples of that. And in showing you the 4 examples, first of all, I'm going to show you what a typical 3-dimensional photonic crystal kind of looks like. So you can see it's very complicated structures, but each one of these has a gap, has a photonic band gap in 3 dimensions. However, and by the way, and also each one of these has some very unusual optical properties that we can explore and discuss. But what's really useful is that it doesn't have to be 3 dimensions. We can go to 2 dimensions, we can simplify the structure, and still, without too much loss of generality, discover properties of these systems that are very unusual, very abnormal. And so they're a lot easier to work with. So from here on, I'm going to be focusing on one of these 2 types of structures to make life easier for us to understand what's going on. So what is this that we've just looked at here? It could be a variety of things. You want index contrast. So every green dot here can be thought of as a rod or a disk, and say it's made out of silicon. Okay. Silicon has an index of about, 3.5 or something, surrounded by air. So air is the low index. It's 1. So we have an index contrast that we need. Think of this as being infinite, top, bottom, and sideways. So we have an infinite periodic structure. Because of that, we have a band structure. And when we can get the button right, there is the band structure associated with this particular system that we're going to be looking at. The blue lines are what's allowed to exist and flow through the material. And we also have a gap, the way we were hoping to. So now let's make a defect. By the way, defects are good things in photonic crystals because they add a new mechanism for controlling light and making it do what we want. So suppose we remove an entire row. So now we've got something that looks like a waveguide moving from the right to the left. And indeed, that red thing here, oops, sorry. The red band here exists inside the gap. And so let's pick one point here and find out where is the light? Where is the light localized with respect to this particular defect? And we find that it exists in air. By the way, this is electric field. So red is positive, blue is negative. And I'm going to use the same color table in everything that I'll be showing from here on. So it's localized in air. Well, already for the cognoscenti in the audience, that's a very unusual effect. We cannot localize optical light in air in any effective way, but we can here. Keep in mind that the only way we have of dealing with optical light in this fashion is with something that's called total internal reflection. This is how a fiber optic works. So a fiber optic is made up of a high index core surrounded by a low index cladding, which is low index or air if you like, and the light gets scattered by bouncing off. That's how the guiding occurs. You can't have the reverse. If I try and do this, the light can't be in the air. It ends up being surrounded in the cladding. But now, for our system, we can. Now, the fact that we can, and also, the fact that we can means that this is, again, a new mechanism for making light do what we want it to do. But why would we want it to do it in air? Well, because light interacts with matter quite a bit. And whenever you have light interacting with matter, you have losses. And in any kind of device that you're making, you want to reduce losses. So maybe by propagating in air, instead of through the material itself, you have a way of reducing losses. And you're going to see towards the end of my talk, this is going to be a crucial point. If we have guiding, we have to also be able to go around corners. We have to be able to turn around. We're guiding something. So if we go back to our, fiber optic cable, we can make, bends like this. If we don't make the bend too sharp, it's okay, so it's fine. But if we make it very sharp, then it won't work. So we're limited to the radius of curvature. In the case of a fiber optic, the smallest radius of curvature tends to be about 1,000 times larger than the wavelength that you're actually guiding. So we'd like to be able to bring that down. So let's go back to our working example and do a 90-degree bend. And now we're going to do a theoretical experiment. We're going to solve for Maxwell's equations, which are the equations that govern light propagation materials. And we're going to send a pulse down here. And we're going to ask, what happens? What do you think happens? Bounces back. No. 95%, more than 95% of the light goes through. And if you take one dot and move it there, 100% transmission. This is an amazing result to be able to do this. And now the question is what's the physics? What happened? Why did this happen? It turns out, and this is very interesting, really, and by the way, there's the wavelength of the light, so you can see the curvature is much smaller than the wavelength of the light. So the answer of why this is occurring can be seen here. The trick is that when light is in guides like this, it thinks it's in one dimension. When it's here, it can either scatter forward or backward. When it's here, it can either scatter forward or backward. So it thinks it's in a one-dimensional world. Now we know from quantum mechanics that if we have electron waves scattering off of a barrier, this is again one dimension only. If electron waves scatter off a barrier and that barrier has a width of integer multiples of half a wavelength, we actually get 100% transmission of the electron. So we know from quantum mechanics this is possible. And the reason has to do with the fact that there's very strong resonant coupling when that condition obtains. So that's precisely why this region here is emulating what's happening in the electronic case. That's the physics behind it. Okay, how about an experiment? So the idea is, so far we did a theoretical experiment. We just did calculations on the computer. So let's do a real experiment. We're going to go to our colleagues at Sandia. We're going to work with Sean Lin. And here is transmission efficiency as a function of frequency. We're going to be working in gigahertz. And we're going to be looking at a square lattice of alumina in this particular case. This is the theoretical prediction that you get 100% transmission here and here. And here's the experiment. Now, to do the experiment, what Sean had to do is take rods of this material, line them up, and basically work in the plane that we cut through the system, and try and keep as two-dimensional as possible in the system. So he removes whatever rods need to be removed, and he gets this. Now it's noisy because this is actually quite difficult to keep everything where it should be, but no question about it, you get 100% transition. Really a unique effect. Next example. Example 2. Explore the potential topological properties of light. In the systems that we've been talking about, the light can go to the left, light can go to the right. But suppose, oh, by the way, not suppose, this symmetry, by the way, is called time reversal symmetry. We call it time reversal symmetry. Now suppose we could break this part. Suppose we had a way of breaking it from going one way instead of the other. The question then would be, number one, can we do it? Can we break it? Secondly, if we do break it, does this now pulse here that's moving along here, is it immune to disorder? In other words, since it's not allowed to interact and bounce back, what does it do? Well, the answer turns out to be, again, from quantum mechanics and from electronic systems. There is a well-known effect called the integer quantum Hall effect. It's a very unusual phenomenon associated with a 2D system of electrons. So we have a system of 2D electrons that are subjected to a perpendicular strong magnetic field. And what this creates in the end is a chiral state. What that means is at the edge of the sample, we have currents that are running around the edge of the sample. And they can run clockwise or counterclockwise depending on the direction of the magnetic field that you apply. And so they did find unidirectional transport and dissipationless effects. And it was David Thouless, actually, who made the connection between time reversal symmetry breaking and the fact that you really have a non-trivial topology of the band structure for this electronic system. Question immediately. Can one extend these ideas now to electromagnetic modes in photonic crystals? Can we make a 2D photonic crystal and get something similar? And the answer is a resounding yes. And these are, I think, the two groups that did it first. There's there's Haldane's group at Princeton, and there's our group at MIT, which involves Marin Soljicic's group. Notice that we published in 2008 in Fusor of Letters. However, the Princeton guys had an archive in 2006, so they beat us to it. But we had a different way of approaching the problem. So I'm going to talk now about how we approached the problem very briefly. And that was to perform a formal mathematical mapping of a photonic crystal system which consisted of a magneto-optic material. Magneto-optic material is one that can interact with a magnetic field. That's why we chose it. And in a DC magnetic field. Here's the, and then we did a theoretical experiment to study what happens if we pour power into the system. Does it, do we get the topological effects that we expect or not? So here's the system that we looked at. So this is a square lattice of yttrium iron garnet, which is the magneto-optical system, in the presence of a perpendicular magnetic field, surrounded by air. Okay? Now what we're going to look at is we're going to explore one of the edges here. And we're going to ask, if we put power inside one of these edges where we expect to have a chiral edge gap, what will happen? Will it move both ways, or will it move only one way, or whatever? So here's our model system. Again, this is a theoretical experiment done on the computer. We're interested in what's happening along here. So we're going to put power over there, as you can see. And we're going to ask, is it moving to the right, moving to the left? Is it moving both ways? First of all, we're going to turn the magnetic field off. No magnetic field, just normal system. And what we're going to find as you can see, light is moving both to the right and to the left. So nothing unusual. This is just the usual thing you'd expect. And there it is. Right? The barrier stops the light. And there you have it. So that's the normal. Now let's turn on the magnetic field. Right away, when you turn on the magnetic field, you see that light is moving to the right, but not to the left. And if we bring that bar down, it's not doing anything. The light is just going right around it. Again, very unusual type of an effect. So all of this was a theoretical experiment. So let's do a real experiment now. So we're going to do something that's called, you're going to use something that's called a parallel plate geometry. It consists of a metal plate on top, metal plate on the bottom. It consists of these yttrium iron garnet rods. If we choose the rods to be a size that's half a wavelength, then the solutions of this system here are identical to that of the 2D system that we've been looking at. So this is precisely what we want to look at. And to give you a more idea of what's around here, this is the waveguide. So light in the gap will be traveling here. Light outside the gap will be able to be traveling here. Here is a scatterer that we can introduce, but we're going to start off by taking it, removing it completely. Okay, and now we're going to put some power in. So we're going to put, We're going to put some power in here, and we're going to put it in at different frequencies, in the gap and outside the gap. And we're going to ask what happens when we do that. If it's in the gap, it's going to be running around this waveguide here. If it's outside the gap, it's going to be going into the material. We expect that as it goes into the material, it comes back to B, and when we go to B to A, we'll get exactly the same thing, because there's no topology there. It's only in the gap. So if we bring the gap in, and plot out what we get, here are the results. As you can see, I'm hiding the gap here. As you can see, the agreement is, for all purposes, pretty good. They agree that there's no topological effects. And now let me remove, by the way, this is the case with no bar. Let me remove this yellow region, and whammo, huge change. You're going from blue, from A to B, but it's impossible to go from B to A once you're inside this waveguide. And if we add the bar, no change. So we've proved the point in a real experiment. Moving now to the third example, we want to understand a case where moving charge particles could be sources of light. Now to do that and make things simple, I'm going to stay in 2 dimensions. I'm going to call it x and z. And in order to find out whether, this is possible, we need to know what light values of omega and wave vector k are allowed in air. Because what values are allowed to exist in air. To do that, we could plot out the frequency expression as a function of the wave vector of light. And as you can see, it's the frequency is equal to the magnitude of the wave vector times the velocity of the light, which is c. If we plot that in an omega kx ky type of arrangement, the light modes are the ones that lie along the cone. So only light that has a frequency omega and a wave vector k that lies on the cone can exist in air. It's useful, however, to know what values of omega and kz do light modes in air exist, regardless of what kx is. And we can do that by just projecting kx onto the kz omega plane. Now this could look complicated to you, but there's only one simple thing that I want you to remember or to understand. And that is when we look at this, if light has an omega and a kz that's in here, we'll see it. If light has an omega out here and a kz here, we will not. That's all you need to know about this. So let's go and look at a particle, a charged particle. So here's a charged particle. You can see it up there in red. And it's moving, say, in the z direction. And I want to understand, can this create light? It's moving at a constant velocity. Can it create light? If we solve for Maxwell's equations, we will find that it does not. But we can come up to this with the same conclusion by doing another simple analysis where we consider phase matching and energy and momentum matching. So this particle here has a, how should I call it? The current density associated with this particle, this red particle, can be written in the following way. It's the charge q times the velocity v times a function that has to do with the localization of the particle. For simplicity, let's assume that it's completely localized to a point. That means we can Fourier transform this. If we Fourier transform this, we find that it's a sum of plane waves, and each plane wave has a value k, and it has a frequency, which is k dot v. So this is what this particle is made up of. And the simple question now is can light with a frequency omega given by v times kz be inside here? And the answer, of course, is no, because v is less than c. V is the velocity of the particle, has to be less than the velocity of light. So it can't do it. So in a simple little analysis like this, we know it's not possible. This was the case until 1934. It was believed to be true. And then there was a shocking result that Cherenkov had discovered, where he was looking at particles like electrons and protons moving at a constant velocity. And when that constant, for different constant velocities, and when that velocity was large enough, he started seeing light coming out, being radiated. So it completely floored people as to how this can happen. And in the end, he actually got a Nobel Prize for this, together with some theoretical colleagues. And the question now is, why? How does this work? Let's use our simple little analysis. He was looking actually at these particles moving in water. Now, water has an index of, say, 1.3 or something, surrounded, like we said, by just through water in this particular case. And if that happens, the velocity of light slows down. So the velocity of light slows down when it's in a material. Because it slows down, that means this edge here comes down. And so now it's possible for a particle to have a velocity v greater than that of light, and at which point you can create the light. And by the way, it's precisely that condition that got them the Nobel Prize. It's precisely that effect. It also has a very striking structure. It creates a forward cone mode, kind of like a, very fast particle moving, through like a shock wave, moving through a material system. 10 years later, Smith and Purcell came back and said, well, wait a minute, you can have it in air as long as it's very close to a periodic structure so that you can think of the whole thing as some kind of crystal. Under those conditions, then you have, the Brillouin zone, like we said, and then when light comes out here someplace, it gets mapped over there and then continues up, so you could still see some light being emitted. And this has a very characteristic a radiation pattern that looks like what we have here. Obvious question. Here are two different systems with two different examples of radiation patterns. What can a photonic crystal do? The interesting thing is photonic crystals have many different types of photon modes. So we might expect to have, a rich amount of different type of effects. So we know that if we want to find a photon mode that has a wave vector k and a frequency that's given by k dot v, we know if that happens, it will be excited. So to do that, we look through the band structure, we look at every one of these states, and we ask which ones have it, which ones don't. We collect the ones that have it, and now we can plot frequency, the amount light that's going to get emitted, as a function of the velocity of the particle. And this is the radiation regime. Now, it looks complicated, but there are four sort of different regions that you can look at, which might give different results. So I'm going to look at now the smallest 1.1, and then go to the highest 1.6. What we're going to do now is look at each one of these modes, and we're going to calculate the group velocity. Group velocity gives us an idea of where the energy is going, what direction it's going, how large that value is. And we're going to be looking at the tips of the vectors to give us an idea of what the radiation pattern might look like, what we expect to look like from the band structure. So here it is for the case of 0.1c. It looks like this. Well, that should be reminiscent of the Smith-Purcell. Looks like Smith-Purcell. And now we're going to do a computational experiment. We're going to send that particle in, and we're going to calculate Maxwell's equations, and we're going to look and say, is anything radiating? And lo and behold, it is. So it's precisely Smith-Purcell. Now let's go to the other end. The other end has a very, very different type of a contour for the group velocity. And now this leads for a forward cone. In fact, it looks like Cherenkov, precisely. So we have one system in having both cases available depending on the velocity. How about intermediate? 0.15 and 0.3. These are more complicated. As you can see here, it's pretty complicated looking, and there's a backward cone that looks like this. And just to make a long story short, Here it is at 0.3. This is a forward cone, but get this, energy is going backward, not forward. This energy going backward is something that's reminiscent of what people think negative effective materials may behave like. But here, we have one system that has all of these, and a lot more depending on how you explore it further. The last example is to look at the traditional dielectric multilayer film. Now, what this is a stack of high and low index material, as you can see here, stacked up like that. It's a very simple structure, right? Layer on layer, layer on layer. And in modern terms, we can think of it maybe as a 1D periodic photonic crystal. The fact that it only has periodicity in one dimension, however, means that the reflectivity is very limited. So it's limited to only the angle of incidence and a few angle degrees around incidence. And there's also the problem that, there's also the problem that there is something called Brewster's angle. That's a particular angle where light coming through for a particular polarization of the light actually goes right through the entire system. There's no reflection. So basically, what's the update on this? Simple structure to make, but reflectivity is really not so good. Because of the range of angles that are not believed to be allowed. This has been was believed to be true for 165 years, since Lord Rayleigh. We discovered, by accident, that this is not true. That in fact, for certain values of index, the parameters that Boyer described this are different values of index and different values of depth. We discovered that there exist actually certain values of N and D where there is a gap for the range of frequencies, regardless of the angle of incidence and regardless of the polarization. So it looks in many ways like a 3D photonic crystal, because any angle, any polarization. That's extremely important because this is a very simple structure to make. Now, it doesn't mean that this takes the place of photonic crystal. It just means that there's more room that you can work with in a system like this. Now, because it was such a big difference in what people expected, we wrote down the theory for this, but it was very difficult to get it published. By the way, this is Josh Wynn. Does anyone know who Josh Wynn is? Hands up. My physics colleagues, yeah. He's an astrophysicist now, but he was a graduate student of mine at the time. So, so we had difficulty in getting people to appreciate it. But one of the authors of that paper was Yoel Fink. And Yoel, as some of you may know, has an incredible drive, and he said, let's do the damn experiment. I think he used that language. So he did the experiment, and here it is. This is for tellurium as a high index, polystyrene as a low index. This is a reflection plotted here as a function of wavelength, in this case microns. This is normal incidence. This is at 45 degrees. S is one polarization, P is another one. I'm sorry for the shaking light. This is 80 degrees, and this is 80 degrees again. And a beautiful, I think, example. Oh, black is theory, dashed is experiment. And this, of course, made it into Science magazine. People started noticing. But more than that, really what amazed me is this next thing. The New York Times wrote an article about it. MIT scientists turned a simple idea into a perfect mirror. So at this point, we decided, well, what can we do with this? What else can we do with this discovery? And we've always been thinking with Joel about rolling it around and making a hollow core. Because we have a good reflector that can reflect in any angle, any polarization, let's do something like this. Hopefully, we can capture light in here, which stays in here because of its reflectivity, novel reflectivity capabilities. So I did a quick calculation, and I found this is power. So indeed, the light beautifully can be created inside this hollow. You can think of this as a fiber, if you like. Of course, this is very limited, what I did here. There's a lot of extra things that one needs to look at. If you make this diameter larger, there are other modes that come in. Are they better modes? Do they have less losses? There are all sorts of very complicated issues to look at beyond this. And that's why I passed this thing on. I did this, but I passed this thing on to my two graduate students to solve the problem. Where are they? There they are. Stephen Johnson and me, and Bayescu, and a few others as well helped out. So while this was going on, Joel was trying to make the fiber, was trying to make this. Now get this, guys. Look at this. This is amazing. So here's a cross-section of the fiber. As you can see here, these lines, we have less than a micron resolution. This is an amazing resolution here. Has been able to. I sound like Trump. I got to be careful. This is This is very impressive resolution. But look here, we're focused at 10 microns. The reason we're focused at 10 microns of light, so we want this particular object, which we call the OmniGuide, to be able to focus and help us control 10 micron light. The reason is because 10 micron light is very sensitive to the skin. So it has very, very low penetration, which means you can do very precise type of surgery, if you like, on human tissue, because it doesn't penetrate that deeply. But also because the power can be very large. And so you can put power through here, which would melt the waveguide. Yet if you do it right and it stays as much in the air as possible, it won't. And that was the next thing that Joel did. So here, it's very hard to see, but here there's a CW, there's a laser with 10 watts. The orifice is about 300 microns. That's about 10 to the 5 watts per centimeter squared. That's a very, very large power density. So it just, melt the material if you just hit it, if you zapped it. Well, here's the movie. So there's the fiber. I don't know if you can see it. See the fiber there coming around. It's bending, it's not melting. And there's our brave student here who's going to, now this thing here is a patch of the material itself. So this is the same thing as the fiber. So all of this was then basically transitioned to a startup company that we put together called OmniGuide. And the idea was to develop basically the world's first precise, flexible, and minimally invasive CO2 laser surgical tool. And it's been used in laryngology, airway, head and neck, otology, neurotology, gynecology, neurosurgery, and spine. And get this, we have an estimated more than 500,000 procedures across hospitals in the US and abroad that have been performed using this. But here now is something even more. CNN had a feature story about using this. We had originally developed it actually as a military device, but then the obvious choice of to use it, for the civilian population was quite clear. And now I'm going to show you the presentation.
The story strikes us, and we think it's going to strike you as well, as remarkable in so many different ways. A military device transformed into a life-saving surgical tool, and a doctor who inadvertently stumbles upon the one thing that holds the key to saving his patient's life.
It's an amazing story.
Sometimes the right information falls into the right hands at exactly the right time. When that happens in medicine, the results can be life-changing. Dr. Thomas Ellis is a neurosurgeon at Wake Forest University Baptist Medical Center in North Carolina. This story begins when a 19-year-old patient arrived in his emergency room. An MRI scan confirmed what Dr. Ellis suspected.
So this is the tumor here.
A very large tumor, right in the center of his brain. A tumor in this location, the third ventricle, is so challenging because to get there requires operating through a long, narrow corridor alongside delicate brain matter.
It became clear to me that this was unlike any tumor I had ever encountered. After trying to dissect the tumor, just 5 minutes with each scalpel, and the scalpel would be dull, and I had to move on to use another scalpel. Went through at least a half dozen of them.
After 9 hours of surgery, Dr. Ellis made the difficult decision to leave most of the tumor behind, rather than risk injury to his patient.
I was just completely demoralized. I really have not encountered a situation like that in 15 years of doing neurosurgery, where I really, in spite of my best efforts lasting most of the day, could not remove any more than 15 to 20% of the tumor. It's just very demoralizing. And while the patient was doing okay, I was really pretty down by the time I got home that night. Being the father of 4 children myself, just the thought of having to go through something like this with one of my own children is just beyond words. I got home, I saw my kids, I read them the typical kind of, end of the night story, and tucked them in bed for the night. And then I went upstairs to my office. I started to catch up on some news at CNN.com, which is pretty much a nightly habit. There was an article in the health section entitled From Military Device to Life-Saving Surgical Tool. My first thought was, I would have given anything to have this tool available 6 or 7 hours ago.
A quick sequence of emails that night put Dr. Ellis in touch with a local rep for OmniGuide, the company that manufactures the BeamPath fiber tool. 3 days later, Dr. Ellis was practicing on the equipment. Originally designed as a military tool for the U.S. Department of Defense, the fiber optic invention just rolled out for neurosurgery 3 months before Dr. Ellis read about it. The streamlined BeamPath fiber allows surgeons to easily manipulate a CO2 laser and bend it to reach almost any tissue in the body. In cases where a scalpel might pose danger, the fiber channels a CO2 laser in a more precise way, melting and then shaving off the tumor.
really about the size and the feel of a fountain pen.
Just 5 days after the first operation, Dr. Ellis was back in surgery for a second time on his 19-year-old patient, this time with the OmniGuide BeamPath fiber.
Over the course of the next 3.5 to 4 hours, we were able to remove the remaining 80 to 85% of tumor that I couldn't have taken out after working most of the day during the first operation. So I made my way to the waiting room to see Bee's mother. It's such a large room, you could see the eyes across the room, and she was looking with some trepidation as I was walking toward her, just not knowing what I was going to say. And, I tried to give her a thumbs up from about 50 feet away and a smile on my face and just let her know we're in great shape. I think it's an amazing story because it's yet another demonstration of how interconnected we've all become in this world. Here you have a CNN reporter in London who writes a story about a neurosurgeon in Chicago who's using a device that was invented in Massachusetts. That story is read by a different neurosurgeon in North Carolina, and all within about 72 hours, we have the device in North Carolina, and in the span of just a few days, we perform really a life-saving operation on this patient.
Of course, none of what I've discussed today and I've done in the past, which didn't have time to talk about, could have been possible without my students and postdocs. And here is a list of my students in pretty much chronological order and where they are now. And I think, as you can see, most of them are actually in academia. There's a large number that stayed in academia, but there's some that are in industry. There's some that involve startup companies as well. And we have, like we saw already, Stephen Johnson and Yoel Fink as on the faculty, as well as at his thesis year as a research scientist. Here are postdocs. Again, a very, very similar effect of being primarily in academia. And of course, where is he? I'm trying to find Marin. He's somewhere here. There he is. And there's Marin here. So thank you very much, everybody. It was a big honor for me. I'm sorry, I forgot. We're from all over the place, but we, on the 70th birthday party, we managed to get together, and there's a picture of us, at least the ones who could make it. So there we are.
Fabulous. Thank you so much.
Thank you.
So you're going to stay here and answer questions, right? Thank you so much. And Professor Joannopoulos will answer questions. If you have something to say, please come to one of the microphones in the aisle, and I'll call on you. And while people are thinking of their questions, I want to take this opportunity to thank my colleagues on the Killian Award Selection Committee for their excellent work in identifying this year's lecturer. And also, I want to invite all of you to a reception following the question and answer in the Nexus, which is the first floor of Hayden Library. Please.
Thank you, Professor. Thank you. Thank you, sir. I'm a student with unslaved.com out of Belfast. I study philosophy, community college, just visiting. I'm a former DoD employee. I noticed you mentioned some historical events, the Schrodinger cat experiment from 1935. You also mentioned Chernkov's Nobel Prize from 1934, a year prior. I'm just curious about the light experiment you mentioned about 30 minutes into your lecture, it's splitting into two, if that applies to the many worlds interpretation of the Schrödinger cat experiment proposed by Hugh Everett in 1957.
I'm not sure I understand the question. I'm sorry.
Well, I'm just making.
Or you're making a comment.
I'm making a comment
Okay,
that
that's fine. Okay.
there are other interpretations during that time in the
okay.
1930s.
Fair enough.
And I just wanted to check that
Fair
Hugh
enough.
Everett, he was a graduate of American Catholic University in Washington, D.C. So
Okay.
the paper you mentioned by Zhang Wang, I believe it supports the many worlds interpretation of that, while there are other German idealist interpretations of what happens when that split occurs as well. Is that correct?
That I don't know if it's correct or not.
Thank
But
you
I
for your,
presume it is. If
thank you
said-
for your time.
Yeah.
Have a good day.
Professor Fink.
Oh,
So, I don't know, is this thing on? No. I guess I first walked into your office maybe in '97. And since then, I could say the world has declined and fallen apart in so many ways. Now, the question I have for you is this, that's an observation. The question I have for you is how in the face of all of this negativity and decline, have you been able to maintain such a positive and optimistic outlook of humans and human nature?
you're serious.
It's an act. Now let's hear that.
That's serious. I'm not sure how to answer that question. Just a matter of believing in the goodness of people and what they can do, what they can accomplish given, and this is very important, giving an environment where they're working in to do research which they feel extremely comfortable in. And that includes also, creating a sense of trust between the faculty and the student, which is key importance. And it's, I think that helps enormously. It's very important for a student to know that they can come up with an idea and it's their idea. And they can, discuss it and bring it up in group meetings, et cetera. And they'll just get help on it. It won't be stolen from them. So I think it's the environment of the group itself that's, I think, key. And I mentioned, I'll give you an example. I mentioned Josh Wynn. How did he become an astrophysicist? What happened was he was an undergraduate at MIT. He worked for me as a Europe. He then worked as a graduate student with me. And then one day in my office, I was asking him, so looking at the future, so what are you interested in? What do you want to do? And he looked at me in a funny way and he said, well, I said, what really excites you in the morning? What physics excites you? And he says, astrophysics. And so I said, so what are you doing working with me? If it's astrophysics. He says, well, I have some pressure from family, et cetera, that maybe it's easier to get a job in astrophysics. In condensed matter physics than astrophysics. And that really struck me as strange, and not strange, but it really hit me he was an extremely talented person who's afraid to take the next step to do what he really loves to do because of the potential of maybe not being able to get a job. So I told him, look, I think you're doing the wrong thing. You should do, if that's what you want, and I'll do it for you. We'll get you to go into astrophysics. And I called Paul Schechter. I don't know if Paul's here. No. But I called him, and he set things up. And eventually, Josh went to work with Paul. He ended up actually working does anyone know it was not Paul that he got his PhD with? you remember? Was anyone write physics colleagues? No. Anyway, so he ended up actually graduating with a PhD from MIT in astrophysics. He left for a few years. He came back, he joined the faculty at MIT. He got tenure at MIT, and then Princeton came along and stole him away.
All right, I think we have time for one quick last question.
Oh, I see. I had a small physics question and a motivation question, which I think would be nice to end on. I think they're both short. If they're long, you can say we can talk afterwards. The physics question was when you mentioned about Cherenkov radiation. I think correct me if I'm wrong, did you say that if you have a particle that travels faster than the speed
Of light.
inside a medium with a higher index of refraction, I'm just having trouble understanding what somebody in that medium of index of refraction would see, because if the particle arrives at the eye of this individual before the light reaches them, then wouldn't it appear that they travel backwards in time, this particle that's moving faster than the speed of light? I was a little confused about that one aspect.
Yeah. So when light travels in a medium, it's not a particle effect. It's a wave effect. The effective wave of polarizing the lattice as it moves in, that entire object that becomes sort of the light pulse that's moving inside the material. That, when it radiates, recall the radiation pattern was like, right, it has a cone and it's moving, yeah. So the particle, I don't know if you mentioned the particle going to your right, its light starts to radiate. I mean, it starts to go along that path that I showed you with the cone, and that's basically it. I mean, you see, and in fact, I think it's blue light. It's peaked at in the ultraviolet, I think. So, which is what you then see. You see something glowing as the particle is moving. As the particles are moving in, if they have a large enough velocity, you actually see them moving and light is being emitted. If they have low velocity, they're moving, nothing is being emitted.
I see. Okay, good. Thank you. And this is the motivational question, which is, you mentioned that your first paper with Josh Wynn and others had a difficult time of being published. I was just wondering if you could comment on the perseverance that you felt during that time in the face of people who might not have believed you and the proposals that you had.
Yeah, that is so frustrating to tell. There's no one, right? We all have published things and we know what it's like when it's hard to get something published. But this was particularly difficult just because they didn't believe it. You know, oh, it's just theory. You know, you have to do the experiment to really show what's going on. But you have to persevere if you believe what it is that you have is correct. Eventually, it happens. In fact, it happened roughly at the same time. You know, we had to be doing the experiment. We did the theory, did the experiment, and it was just after that, being in Science magazine was the huge step forward for us. And you know, then having the New York Times take over the process from then on to try and propose it and present it as something very new and exciting was absolutely fantastic for us.
Thank you.
Thank you for sharing the magic.